Yeah, good morning. Today we're going to start talking about Chapter 5. The title of Chapter 5 is Discrete Probability Distributions. And the title of Section 5.2, which is of course the first section of Chapter 5, is entitled Probability Distributions. Well, before we start talking about probability distributions, let's talk about random variables. Right? A random variable is a variable whose value is determined by statistical experiment, or more informally by chance. A discrete random variable. Well, it's a random variable that has a finite, or some say countable, number of possible values. Okay. Alright, so for example, if we let x equal the number of heads in two flips of a coin, of a fair coin, we see that x is a random variable. X can attain any of three values, namely 0, 1, or 2. Now, because x is a discrete random variable with a finite number of values, that means we can list those values. Right? X can be 0 heads in two flips, you can have 1 head in two flips, or you could have 2 heads in two flips. Alright, we can assign to each of these possible values of x a probability. Well, we know in two flips of coin we've got 4 possibilities. Tails, 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 heads, heads, tails, and heads, heads, right? Alright, we can then assign probabilities. The probability of 0 heads in two flips, well, that's going to be 1 out of 4, or 1/4. The probability of 1 head, well, there's 2 ways to get 1 head, tails, heads, or heads, tails, so that's 2 out of 4, or 2/4, and I'll leave the fraction unsimplified for the moment. And the probability of 2 heads in two flips, well, there's only 1 outcome out of those 4 that has 2 heads. Alright, so we can then construct this probability distribution, just like a cheese slicer slices cheese. A probability distribution distributes 1 unit of available probability amongst all possible values of a random variable. Note, because we have encompassed all possible values of x in this list, the associated probabilities must add up to 1. So let me summarize that in mathematical style. Summation p of x equals 1, must always equal 1 in a probability, in any probability distribution. I'll abbreviate that DIST. Also, please note that each probability must be between 0 and 1. And again, that holds for any probability distribution. In a probability distribution. So I'll abbreviate that prob disc, or dist, if that's all right. Let's look at another probability distribution and another different random variable. I will let x equal the number of girls in 4 births. And again, we're going to assume a boy or a girl is equally likely in any birth. Alright, if you've got 4 births, well, you've got 4 slots to fill in with 2 possible outcomes in each slot. So 2 times 2 times 2 times 2 is going to be 16. 2 to the 4th power equals 16 possible outcomes. And I'm not going to list them all here. It's just too tedious. Boy, 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 boy. Boy, 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 girl. Boy, boy, girl, boy. We could keep playing this game until we finally exhaust all outcomes with girl, 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 girl. Okay? 16 possible outcomes having 4 births, allowing any child to be of any gender and in any order. Let's construct the probability distribution for x. Alright, so what I'm going to do is I'm going to make a table. X is a discrete random variable because x can take on a finite number of values. Well, we're taking on, let's see, number of girls in 4 births. What's the minimum number of girls you can have in 4 births? That, of course, is 0. You can have 1 girl in 4 births. You can have 2 girls in 4 births. You can have 3 girls in 4 births. And, of course, you can have a maximum of 4 girls in 4 births. So we've got 5 possible values for our number of girls in 4 births. Alright, well, let's think for a minute. I think we can fill in all these without brute force, writing down the sample space entirely. Let's see, 0 girls. If I've got 0 girls, that means I've got all boys, and only one of those outcomes has all boys, so 1 out of 16, or 1/16th, will be that probability. Alright, let's go on. If I've got 1 girl in 4 births, well, 1 girl means you've got 1 girl in 4 possible slots, 4 possible places for that 1 girl. Hence, you've got 4 out of 16 outcomes will have 1 girl. Hence, a 4/16 probability of 1 girl. Alright, let's leave 2 for a moment. I'm going to go on to 3 girls. Well, if you've got 3 girls, that means 1 boy. And similarly to the 1 girl case, you've got 4 possible slots for that 1 boy. Hence, 4 out of 16 outcomes have 1 boy, or a 4/16 probability for 1 boy. Let's see, 4 girls. Let's do 4 girls. 4 girls, well, only one of those outcomes has all girls, and that's 1 out of 16th, or a 1/16th probability. Now, 2 girls is a little more difficult, but the easy way to fill in that cell is to note all the probabilities must add up to 1, so I can add up the cells we have filled in and subtract from 1 to get that probability of 2 girls. Let's see, I've got 1/16th, 5/16, adding them up, 9/16, 10/16. All the other cells add up to a 10/16, so this missing cell has to have a 6 out of 16 probability, or 6/16 probability. Right, I'm leaving these fractions unsimplified for demonstration purposes, and please convince yourself that all these probabilities in this probability distribution add up to 1. Alright, let's go on. Now let's consider, again, the probability distribution for x equals the number of girls in 2 births. We've already looked at that earlier in the class. Now, logic equivalent of flips of a coin, two heads and one coin, or two flips of a coin, a fair coin. I'm going to fill this in. Right, as we saw for, well, again, equivalent to number of heads in two flips of a coin, really, assuming boy and girl are equally likely in any birth, the probability of 0 girls in 2 births is going to be 1 out of 4, or I'm going to decimalize it as 0.25. Right. If we need to refresh our memory, let's see, I can have boy, 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 girl, girl, boy, or girl, girl, right? Alright, the probability of 1 girl in 2 births, well, I've got 2 possible outcomes that have 1 girl. So 2 out of 4, or 2/4, is equivalent to 0.5. And if I've got 2 girls in 2 births, well, only one of those outcomes has 2 girls. So 1 out of 4, or 1/4, or 0.25 probability of 2 girls. Alright, so let me ask a question. With this very simple probability distribution now, I'll ask you, what is the mean value for x? And this is largely a theoretical concept. It's really your theoretical mean or average outcome for infinitely many trials of this experiment. So it's largely an abstraction. Similarly, I might ask, what is the standard deviation? Not of raw data, as we saw in earlier chapters, but the standard deviation of a probability distribution here. All right, these are 2 questions which we are going to seek to answer in the next part of this section. I'm going to give you 2 formulas. One's simple and one's a little more difficult. The mean of a probability distribution. Alright, we're going to label this as mu, just like we would label a population mean. But the formula is different. What I do is take each value, weight it, or multiply it by its associated probability, and then add them up. So summation x times p of x is our mean for a probability distribution. Okay? How about the standard deviation? Of a probability distribution. Again, I label it with the same label as a population SD. Now hang on, this formula is a little more difficult. I square each data value. I weight that squared value by the probability, or multiply it by its associated probability. I add up those products. Then I subtract the previously computed mean of the probability distribution, and then take the square root of that entire expression. So that is our standard deviation of probability distribution formula, and if you stare at them long enough, they should look somewhat familiar to the formulas for mean and SD of raw data, but certainly very different. All right, let's apply these 2 formulas in a simple example. Again, I'll take that probability distribution above for the number of girls in 2 births. Copy it down for me a minute. And I'm going to decimalize some things here. 0.25, 0.5, and 0.25. Alright. Find the mean and the standard deviation. Find mu and sigma for this probability distribution. Alright, to this end, I'm going to add a couple of columns here. I don't have to do it this way, but I'd like to do it this way. Alright, to find the mean, I'm going to have to take each x value, multiply it by its associated probability, and add up those products. Well, this I can kind of do in my head here. 0 times anything is 0, so that cell is easy. 1 times 0.5 is, of course, 0.5. And 2 times 0.25 is, of course, 0.5. Alright, so all I really need to do for the mean is add up these products. Summation x times p of x is going to be 1, so the mean for this probability distribution is 1. And that does kind of make sense. If you look at the probability distribution, it looks symmetric, and it looks like the central value, this is at 1. The strongest, most likely, highest probability value of x is 1. So certainly it goes along with the first glance at the probability distribution. Alright, so mu is done. Now we got to find sigma. Well, I'm going to add another column here. I'm going to call it the x squared times p of x column. Because you recall that formula for standard deviation of a probability distribution does involve adding up squared values of x multiplied by probabilities for that x. Alright, let's fill this in cell by cell. 0 squared is 0. 0 times anything is 0, so that's easy. About 1 squared times is 1, and 1 times 0.5 is 0.5. So that one's easy also. How about 2 now? 2 squared is 4, and 4 times 0.25 is going to be 1. Alright, I'm ready to add up this x squared times p of x column. And of course it's 1.5. Alright, we're almost there, not quite. We need to plug this value of 1.5 in for this expression in that standard deviation formula. So let me go ahead and do that. Again, this goes here. So 1.5 is that summation, sum of that third column, minus, don't forget to subtract, the mean of the previously computed mean. So my standard deviation will be the square root of 1.5 minus 1 squared. 1.5 minus 1 then, and 0.5, the square root of 0.5 would be 0.707. So there is the standard deviation of my probability distribution. Alright, the book may sometime ask us for the variance. And again, variance doesn't really have its own symbol. It's simply the square of the standard deviation. Well, this variance will then be 0.707 squared, or 0.5 for this example. Okay? Now let's try another one. Get a fresh screen here. Alright. Let x equal the number of girls in 3 births. And I might ask you to construct the probability distribution for x and compute the mean and the standard deviation for that probability distribution. Alright, if x is the number of girls in 3 births, x can take on 4 values, right? 0, 1, 2, 3. each of those values of x occurs with a different probability. If you've got 3 births, you've got 8 outcomes, from boy, 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 all the way down to girl, girl, girl. I'm not going to write out all the possible outcomes here. It's just too cumbersome. I've got 8 outcomes possible. Alright, how many of those outcomes have 0 girls? Well, only 1 out of 8 will have 0 girls. How many of those outcomes will have 1 girl? Well, if you've got 1 girl, you've got 3 slots for that 1 girl, divided by 8 possible outcomes. Let's see, 2 girls. 2 girls means 1 boy, and again, 3 possible slots for that 1 boy, so 3/8 probability for 2 girls. And 3 girls, well, only 1 of those outcomes out of 8 can has 3 girls, right? 1/8 probability. Alright, I want to now compute the mean and the standard deviation. So I'm gonna make 2 more columns here. Well, to compute the mean of the probability distribution, I'll need to take x times p of x. Let me do that first. Well, 0 times 1/8 is 0. 1 times 3/8 is 3/8. And I'll leave these fractionized. I think I can handle these values fractioned as fractions for this particular example. 2 times 3/8 is 6/8, and I'm going to leave them unsimplified for later purposes. And 3 times 1/8 is 3/8. If I add up this column, let's see, 3/8, 6, 7, 8, 9, 10, 11, 12, it's 12/8. So mu is summation x times p of x, and 12/8 of course reduces to 1.5. So the mean for this probability distribution is 1.5. Let's make another column here to compute the standard deviation. I'm going to need an x squared times p of x column. 0 squared is 0, and 0 times anything is 0. 1 squared is 1, and 1 times 3/8 is 3/8. Multiplying that squared value by the associated probability. It's 3/8 there. That doesn't look good. Let me do that again. Running out of room here in these small cells. Looks better. 2 squared is 4, and 4 times 3/8 is 12/8. And again, I'm going to leave things unsimplified for the moment. 3 squared is 9. 9 times 1/8 is 9/8. Alright, so if I add up this column, summation x squared times p of x, let's see, I've got 3/8 plus 12/8 is 15/8 plus 9/8 is 24/8. Well, 24/8 is 3, is it not? Alright, so I'll now go to my standard deviation formula for a probability distribution. It's square root of summation x squared times p of x minus the previously computed mu squared. Alright, so this goes here. Alright, the sum of that fourth column is 3. So I'll have the square root of 3 minus, remember the previously computed mean was 1.5, so 3 minus 1.5 squared. Well, 3 minus 1.5 squared, according to my calculator, is 0.75. Don't forget to take the square root. Alright, so the square root of 0.75 is 0.87. So I've constructed the probability distribution given this random variable and computed the mean and the standard deviation. Alright, let's go on to another example. Again, I mentioned this before earlier. I'll say mu. Of course, we know mu is the mean. In this context, it's the mean of a probability distribution. largely theoretical value, and I'll say this is the theoretical, spell it right, theoretical mean outcome or average outcome for infinitely many trials. Infinitely many trials of any particular experiment. This mean is also known as expected value. I think the way the author breaks it down, usually expected value is denoted with E, cap E. Now, mu is exactly the same as E. I think our author invokes the E terminology when he's talking about games of chance. Alright, so let's take that author's convention and embrace it in this example. Perhaps an interesting, I like to think this is an interesting example. Kind of blows the magic away from games of chance. Let's start with the event of playing a New York State daily number. Now we're going to simplify the rules of the New York State daily number a little bit here. Right, I'm going to say to play the New York State daily number, we pay, not play, we pay $1. You pick a 3-digit number. And if the pretty girl on TV picks that same 3-digit number, in other words, if your number hits, you win $500. I know the actual New York State daily number game is a little more complicated than that, but again, we're simplifying this here for our purposes, for our example purposes. Okay? I'm going to define a random variable here. Let x equal the net winnings in your game in dollars. And I'll say construct the probability distribution for x and compute the expected value. For x. Alright, this may be a little simpler than you think. Well, if you're talking about net winnings in this game, well, x can take on two values. You either win or you lose this game, right? Now, x can take on two values. Now, if you play this game and lose, you lose your dollar, so I'm going to let x be -1 because my net winnings then would be a -$1. Okay? Somewhat similarly, well, let's say you play this game and win. If you win $500, but remember it's net winnings, so I've got to subtract off the dollar that I spent to play. So in case I win, my net winnings would be then $499 in dollars. Alright, both these outcomes occur with different probabilities. Now let's say you lose the game. Well, how many 3-digit numbers are there? Of course, there's 1,000 of them, from 000 to 999. So I've got 1,000 possible outcomes in picking a 3-digit number, and 999 of them are losers in this game, right? Similarly, if I want to win this game, well, you've got 1,000 chances to win, and only one of those numbers is a winner. Alright, so there is my probability distribution for x. Alright, now I want to compute the expected value. Well, remember, the mean is the expected value. Again, the author's convention is to talk about expected value when he's talking about games of chance. So all I need is to multiply each possible x value, and multiply by its associated probability. Alright, so let me make a third column here. X times p of x. I'll get minus 1 times 999 over 1,000. That's minus 999 over 1,000. How about down here? 499 times 1 over 1,000 is going to be 499 over 1,000. And if I add this third column now, summation x times p of x, forget about the sign here, minus 999 plus 499 over the common denominator of 1,000 gives me negative 500 over 1,000, which of course is negative 0.5. Well, negative 0.5 what? Negative $0.5. Remember, your x values are in dollars, so your expected value will also be in dollars. And believe me, that negative sign is not there by accident. This negative $0.50 or negative 50 cents is what the house can more or less count on for every play of this game. And really all casino type games of chance, all these lotteries, whatever, you can rest assured that if you grind it out, they will all have a negative expectation, meaning that the player can usually expect to lose in any given play of the game. Alright, so this negative $0.50 for this New York State daily number expectation represents a theoretical mean value for infinitely many plays of the game. Write that down. Infinitely many plays of this daily number game. Alright, one more subtopic I want to talk about before we call it a day is unusual values. For a random variable or probability distribution. Well, what we're going to do is somewhat arbitrarily set up what the book calls a range rule of thumb. Unusual values for a probability or for a random variable x. We're going to say in a middle of the road range, we're going to say values of x are usual. And beyond that middle range, outside high or low, we're going to call these values of x unusual. Okay? How we set up those boundaries, again, is based on mean and standard deviation for the probability distribution. Right? Mu minus 2 sigma is 2 SDs below the mean. Mu plus 2 sigma is 2 SDs above the mean. So if your random variable value is beyond 2 standard deviations from the mean, we call them unusual, high or low, right? Let's look at an example of this. Let me get a fresh screen here. Example. I'm going to say let x equal the number of games in a World Series baseball contest. As you may or may not know, World Series are defined by what they call a best of 7 competition. The minimum number of games you can have in a World Series is then 4. Right? The first team to win 4 games in a World Series wins the World Series and the contest is over. Alright, so the minimum number of games in a World Series is 4, and of course the maximum number is then 7. Okay? Once you've reached 7 games, someone will have had to have won 4 games, right? Alright, we're going to look at some raw data here. Now, each of these probabilities are computed based on a study of all previous World Series of all time. So we base our probabilities on the past history of the game. All right? And I'm going to ask 2 things. A here, find the mean or expected value of x, or of this probability distribution. And then B will ask, is it unusual to sweep a World Series by winning the first 4 games? Okay? So anytime you're given a probability distribution and you're wondering about usualness, well, you're going to have to compute the mean and the standard deviation. Alright, the mean for this probability distribution, well, it's summation x times p of x. I take each x value, multiply it by its associated probability, and add them all up. Alright, let me make a column here. I'll have an x times p of x column, and 4 times 0.19 equals 0.76. 5 times 0.22, 1.1. 6 times 0.23 equals 1.38. 7 times 0.36 equals 2.52. So if I add up this column, I get summation x times p of x. So 2.52 plus 1.38 plus 1.1 plus 0.76, and I get 5.76. So there's my mean value for x. And it kind of sits around right about here, right? And judging by a first glance of that table, that looks kind of like where it's supposed to be. Alright, so we found the mean of the probability distribution. Now we have to ask, is it unusual? Well, we'll also need the standard deviation, right? Well, the standard deviation, I'm going to need a third column here. Let me erase this stuff here because I need a fourth column here. X squared times p of x will give us, well, let's see, 4 squared is 16. So 16 times 0.19 is going to be 3.04. Similarly, 5 squared is 25, and 25 times 0.22 gives me 5.5. Now keep as much decimal accuracy as you can stand here. 36 times 0.23 will be the next cell. It'll give me 8.28. And then 7 squared is 49, and 49 times 0.36 will give me 49 times 0.36. Hang on, I made a mistake. 49 times 0.36 give me 17.64. Alright, so if I add up this column, summation x squared times p of x equals, I get a 34.46. Alright, so now I'll want to go to my standard deviation formula. square root of summation x squared times p of x minus mu squared. I'll take square root then of 34.46 minus 5.76 squared. Now if I grind that out, I get a standard deviation of a 1.13. Alright, so now I have to ask myself, is a value of sweeping the World Series, or 4, a game length of 4, unusual? So let me make a little bit of a mini number graph here. Remember, if you're more than 2 standard deviations away from the mean, high or low, you are unusual in your result. Alright, so I'll take 5.76 minus 2 times 1.13 to establish a lower bound for my usualness, and that says 3.5. Alright, mu plus 2 sigma, that's going to be 5.76 plus 2 times 1.13, and that gives me an 8.02. Should be a 0.2 there. 8.02. So these are my boundaries. Now if you win the World Series with a sweep, you win the first 4 games, and certainly 4 is, or 4 games, not 4 wins, 4 games. 4 games is within these bounds of being usual. Right? Anything out here would be unusual and unusual. So part B says, is it unusual to sweep a World Series? And the answer here is no. Okay? Because the x value of 4 is between these boundary values. Alright, we'll call it a day. It's about 42 minutes or so. So this concludes section 5.2, probability distributions.